This video is going to cover Unit 25, Section 6, Circle Tangents and Chord Segments. Alright, near the top of page 629, we've got a blue box, and in that blue box it says, a line perpendicular to a radius at its extremity is tangent to the circle. Okay? What that means is that this is a radius and this is the radius extremity. So when this line right here is perpendicular to the radius, then that means that this line is a tangent line. Well, we've already mentioned tangent lines before. So this line is a tangent line because it is perpendicular to the radius at the edge of the circle. That's effectively what it's talking about. Then it says that a tangent to a circle is perpendicular to the radius at the tangent point. So both of these lines are tangent lines and they are perpendicular to the radiuses. Okay? So let's take a look at an example of that. We can find an example of that at the bottom of that page, figure 25-50. Okay, so our goal here is to find the distance from this point to that point. All right, so we have this, so we know that this is a right triangle right here because we know that this is a tangent line. It says in the instructions that AC is tangent to the circle. So that means that this is a 90-degree angle right there. So that's a right triangle. We know this side, 9.25, and we also know this side from here to here. It's 7.35. Remember, all radiuses are the same. So if this radius from here to here is 7.35, then this one from here to here is as well. So we have a Pythagorean theorem problem. So I will say the square root of 7.35 squared plus 9.25 squared is 11.81. 11.81. And that is how they worked it out right there. 9.25 squared plus 7.35 squared equals that, and then they took the square root of it. So that's how we use that. Okay. All right. So the next page, at the top of page 630, it says, two tangents drawn to a circle from a point outside the circle are equal and make equal angles with the line joining the point and the center. What in the world does that all mean? So if I have a circle, center point right about in there somewhere. Then I have two tangent lines coming to a point. We'll put that point right there. Tangent line. Tangent line. That point's getting bigger. Okay, so what that means is that because these two lines are tangent, they are 90 degrees from the radius that meets them at that tangent point. So that means that this angle is the same as that angle. This side is the same as that side. That's what that's talking about. So let's take a look at figure 25-52, and let's do some applications with that one. Okay, that one right there will work. So what I have then is a point right there. Center point right there. Not really to scale, but that's okay. Okay, so what we have here is we have a distance from there to there as 52 feet 9 inches. And we have a radius of 34.5 feet, or 34 feet 6 inches. So that's 0.5. I'm going to convert everything into inches. Now, what we have is some kind of a flower garden, and we have point P right here, point A right here, and point B right here. We have a walkway from A to P to B, and we want to know what that distance is. All right? Yeah, that's what they're looking for. Now, AP is equal to BP. So how do we find that distance right there? Well, let's take a look at this. Okay, so look at this right triangle only, right here. All right? So I know what the hypotenuse is. The hypotenuse is this. I know what this leg is. This leg is that. So 52.75 feet is what that is. Now, to find the distance from here to here, I say that PB is equal to 34.5 squared. Oh, you know what I did? I went the wrong way with it. PB is equal to 52.75 squared minus 34.5 squared. See, I would have come up with a negative underneath the radical, which I mentioned before, that you would right away know that you did that the wrong way. So the bigger number has to go first, or you'll figure it out. 52.75 squared minus 34.5 squared, and that gives me a distance of 39.9. So that means that PB is 39.9 and PA is also 39.9. But they want to know the distance all the way from this point to that one. So 39.9 times 2. Probably could have just done that one in my head. 79.8 feet. Ta-da! That one was fun. And now, the next one is in a combination with at the bottom of page 630 and top of page 631. If two chords intersect inside of a circle, let me get that situation first. So we've got two chords, do here, and let's draw this one here. They intersect inside the circle, so A We'll call that C because it's in the center. We'll call that B. We'll call this E. And we'll call this X. Okay. What we have here is the product of these two parts is equal to the product of these two parts. So, in other words, AC, that distance AC, times BC will be equal to XC times CE. So this distance times this distance will be equal to this distance times this distance. All right? And we will have an example of that. Let's turn to page 633 at the very top, figure 25-60. I'm going to go ahead and get a new, erase all of that, and oh wow, I erased it. It was perfect. All right. This one looks like fun. So does the next one we're going to do. I think we'll do it. This one actually extends out, but we don't. Okay, so this is X. This is what we're looking for right there. And we've got, this is awful close to the center, but it shouldn't have been. Okay, the center should be down below. And that is O, M, T, S, and this point is point P. Okay, so this distance right here is 1.2. The distance from here, I'm going to draw it. I just draw it out right to there. 1.9. So 1.2 is from there to there, and 1.9 is from there to there. And this is point E. And then the distance from here to here is 0.614. Okay, I think that's everything. Not exactly the way they did it, except for the diameter is equal to 2.62. Now we know that SP times MP is equal to X times PE. Okay, so we know this is what we know. All right, so let's go ahead and see if we can figure out what some of these things are. So that's the one we're not going to be able to find until we do the multiplication here. So let's take a look at PE from here to here. Well, if this whole distance is 1.9 and this is 1.2, so that means that PE is 1.9 minus 1.2, which we can say PE is equal to 0.7. Okay, so we got one of them. So MO, let's just go ahead and say the radius is 1.31. Yep, did it in my head, just like that. So the distance from M to P is this plus that. .614. 1.924. So that means that MP is equal to 1.924. So the idea here is that I start my equation with all of the variables that I need to have in there, and then I go about using the numbers that they're giving me and finding out what each segment is. So now I need to find SP. Well, SP is the radius, because I know it doesn't look like it, I drew it a little bit wrong, but the radius is from here to here. And we know that that radius is 1.31. So now what I'm going to do is I'm going to subtract off this right here from 1.31. So 1.31 minus 0.64, oops. .614. So that means that SP is equal to 0.696. So I have 0.696 times 1.924 is equal to X times 0.7. So that means I just simply divide this by 0.7. Fun with calculators today. Fraction bar 0.696 times 1.924, 0.7 in the denominator, 1.91, and it probably said round it. 1.913, 3 decimal places. Ta-da! That one's fun, sort of. But, like I said, I started with the equation. This times this is equal to this times that, or that right there. And then I go about using the numbers that they give me to find each of those dimensions and then solve for the one that I have to solve for. All right, the next one we want to look at, well, maybe the next one we're going to look at, whether we want to or not, is going to be number 14 at the bottom of that page. And I need a decent one to start with. You know, a little bit smaller. Yeah, that'll work. Well, that's almost perfect. Whatever you do, don't look down. Oh, I should have extended that a little bit. And then a little out. Okay, that is absolutely perfect. At least, well, I got my crooked glasses on. Okay, so we've got this line coming down here. That's a tangent, okay? I'm pretty sure it says it in there. And that's a tangent right there. We have radius is equal to 0.8. We've got the distance from here to here is 1.5. The distance from here to here is 0.52. The distance, let's see, what else do we have? We have the distance from here to here is 2.865. So what I'm looking for here is x, which is the distance from right there to right there. Now, it might look like it the way I've drawn it, that this center point is above that, but it's not supposed to be, okay? It's this distance, this right here is not lined up at all with that center point, okay? It is, the center point should be drawn a little bit below that. Okay, so what we need is, let's just examine this for a moment. If I have this distance right here, then I can add this distance and this distance from here to here, and I would have the total distance from this top, very top, to the very bottom. And if I have that total distance from the top to the bottom, then I can subtract off this distance right here to get x. Okay, so my first initial goal is to find the distance from here to here. Well, this is 1.5, and this one is 0.8 because the radius is 0.8. All right? So I use the Pythagorean theorem. This is the hypotenuse because it's opposite to 90. So hypotenuse, we'll call that side, might as well call it side C. Side C is equal to 1.5 squared plus 0.8 squared, and then the square root of the whole thing. So the square root of 1.5 squared plus 0.8 squared is 1.7. Um, 1.7 right there. Okay, so now that I've got this distance, I can add this one plus this one. Well, 1.7 plus 0.52 plus the distance from here to here, remember, is a radius, and we already know that to be 0.8. I don't like to try all that in my head. There's already enough stuff in there. .02. So the distance from here to here is 3.02. So that will give me x. Keep that on the screen. 3.02 minus 2.865. Oops. Still got to hit the right buttons. .155. So that's what x is, 0.155.